Thank you very much for coming to my talk. My name is Sam, and there it is. Yeah, I'm a data engineer at Discovery, the channel. Before that, I was a lead engineer at Just Eat, and the inspiration for this talk actually happened at Øredev last year, because I was 2 years into my transition from being an API.NET developer to working exclusively with big data. And a bunch of the speakers said, well, why don't you give a talk? A lot of people are hoping to transition to that industry. Out of interest here, who here actually is thinking of moving to big data or has moved to big data? Okay. I literally can't see anyone, so I shouldn't have asked that question. I think it was like 7 or 8. That's fine. It's okay. So why I changed careers? So traditionally, I was writing APIs, and I realized that there was a wealth of data in the messages throwing through our e-commerce system. And I was going to the team and saying, well, we're not utilizing this data. Right? By the time it reaches BI, a lot of the metadata around orders, a lot of the metadata about users, the customer behavior in your system has gone. And data is really the unique selling point. You know, companies like company A and B, the difference between company A and B isn't the tech anymore. You know, companies like WhatsApp and Instagram sold for billions of pounds, not because of their technology, not because Facebook couldn't write an image classifier or a chat app, but it's because they understand their customer behavior, and that's what to me is a unique selling point. So because of that, I was asked to lead a team in the BI section of data engineers and bring in certain data principles or certain engineering principles that we think of as bread and butter into the data world. But the first question you sort of ask yourself is, what is big data? And I kind of like this tweet because I'm not going to say it out, but I guess people will see it in the video. But it's because no one exactly gives it a strong definition. Everyone wants to say that we're doing big data now, it's the new cool world. Before that, it was microservices, and before that was something else. But there has been a definition by IBM, which is down to the 3 V's. And the first is the volume, how much data you're going through. We're talking about, out of interest here, how many think 100 gigs is big data? Terabytes, hundreds of terabytes, petabytes. Actually, it doesn't actually matter, because the definition of big data is it can't be handled in a single node. But volume, how much data you're going through, is one of the 3 key definitions. So the size of it. The second is, it's a bit strange, this clicker is not working very well. But the second is velocity, how fast this data is coming through. Is it once a day? Is it once an hour? Is it once a minute? Once a second? How fast this data is coming through your system and into your pipeline? And the last is variety. How many different data points do you have? Is it mainly your platform? Are you talking to other things like API, Google APIs, or Facebook, or Twitter, or payment providers? How many different data providers that you have, and what it means to your business and how you integrate it. So when I first came in, there's few terms that I had to learn, basically. And the first and most important one, what you do day to day, is ETL. And what it means is extract, transform, load. So you extract the data from a certain area, you transform it to shape it into the business language, your domain language, if you're familiar with DDD, the ubiquitous language, and you load it into a data warehouse. And that's what I found. I found that we were using Redshift as a data warehouse. And for those of you who don't know the difference between a database and a data warehouse, is a data warehouse is aimed directly at people reading from it. So it's OLTP versus OLAP, online transactional processing, which is traditional SQL databases, versus online analytics processing, which is people reading. So that's data warehouses like Redshift, Postgres, which is what Redshift is based on. And Redshift is sort of the de facto technology that people use at the moment because it's on AWS. So if there are more people reading from the tables, then it's OLAP. If it's more writing, when it's more transactional, then it's OLTP. So the state of play was our BI team was using Redshift as our data warehouse. But I came in and realized all our ETLs were just a bunch of Python scripts written by Python developers that are meant to move data from A to B, do a bit of transformation on it, but it's not really maintainable. It was very difficult to understand, very difficult to reason with. I thought dealing with monoliths back when we were dealing with web service and APIs was difficult, but this was a monster. It was completely hard to understand and change. It was all hard-coded to a Windows box, and this box would just do the ETL and then push it to Redshift. The problem is, if that box died, that's it. That's the entire thing dead, right? And I said, okay, the first thing we're going to do is let's just get immutable infrastructure here, because that's a massive source of failure, basically. If that fails, everything dies. And AWS will restart that box once every 2-3 weeks for security. And at the time, we were like, why? Don't restart it for security. But then the NHS happened, and then we realized how important security was. So the first thing we did was to solve that was we said, okay, we're going to run it on an immutable infrastructure, run it as it is, but constantly running all the time, kill off as soon as it finishes running, kill it off, run it anew. So that way you avoid Snowflake service. And so you sort of know this when you're building normal APIs, but traditionally, data developers don't. The next problem we faced was, now that we had it running in Linux and it's running and spinning up machines whenever you want, is the fact that it was incredibly slow to run. It took 9 hours to run one job, from start to finish, because we were running 18 or 19 different databases, extracting from there, as well as the different APIs we needed to call. And even if something fails, like the security update, or we pushed a change that failed, we don't find out about it till the next day. There was no alerting at all in place, other than emails, I guess. And it took, even if we fixed it within 10 minutes, it took another 8 or 9 hours to run. And it was ridiculous. So we try and work with the DBAs and say, well, why can't we just add a last updated flag and then just take the deltas? So that's a simple thing. Then some of the APIs that were writing the databases were written, the SQL queries were written badly, whether they're using ORMs or not, I'm not sure. But they were doing select stars, and it will break the APIs. We tested it in a dev environment. So to fix that, we looked at change tracking control, which is something that SQL Server gives you. But the idea is you point it to certain tables that you want change tracking control on, and it will add the primary keys and the date they changed. So you insert anything to a table or you update, takes that primary key ID of what you changed, and puts it in an audit table. And then you query this audit table to say, give me the last 15 minutes. And that's what we did. A problem we faced is the longevity, or how long this data lives in this audit table. You can set it up to a day, 2, a week, it's up to you. What you don't have control over is when Microsoft SQL Server says, clean up that table now. It's been X amount of days. I don't need that data. Get rid of it. And because you don't have control, it will really affect performance of your platform. Remember, these are on the transactional databases, these control tracking. So it will clean up during peak time, and it adverses performance. So we had to sort of refactor that to use certain triggers to push to these audit tables rather than change control. So that way we have control of the schedule of cleanup. We have responsibility to say, okay, clean it up. The next problem that we face is new sources were extremely painful to do. And by new sources, I don't mean a different data provider. I mean, imagine your website said, okay, we're going to assume that if we implement Facebook login, we're going to get more orders because people don't have to sign up. And it's a lower barrier of entry. And remember, everything we do in IT is assumptions. We assume if we do A, we'll get B. We have no guarantees. Some are good assumptions, some are bad assumptions. And that's where data comes in. You use data to make your assumptions. And that's where A/B testing comes in. If you do A, you see the results, and you're like, okay, that guarantees that's right. But again, it's an assumption before you started doing it. So imagine we implement this, the engineers go off and implement Facebook login, right? And I'm going to use this example throughout the talk, but that now the APIs that are responsible for authentication or logging in says, okay, this was a Facebook user. or the thing that's responsible for telling you about orders is now this is a Facebook login order. The engineers go off and implement it, and then maybe 4 or 5 weeks later, the business comes out and says, okay, how did we do? They don't go to the engineers to ask them how we did. They go to BI, right, and say how we did. And then BI are like, well, we implemented Facebook login. We didn't know. So they go to the data team and say, like, we've got to get that data. And now it's been 4 or 5 weeks, and that's a failure of communication. But now you can't, even if you start implementing it, with traditional databases, you have to add that new column in that table, create a new temp table with the new column, copy the data from the old table to the new table, and then drop it, because that's how they're designed, the analytics processing data warehouses. Even after you do that, which takes about maybe 2-3 hours, it's annoying, but it does happen, you still have to backdate it, because you don't want the data from today, you want the past 6 weeks or the past 5 weeks that you've been working on, because then you want the analyst to be able to do that. And it was really painful. And that's where we realized, you know what, we've reached a point where we can't rely on these Python scripts. They are not fit for purpose. So we're like, okay, we're going to build a data pipeline, right? And use technologies that are specifically meant for big data. Distributed systems to where the data is being distributed, and we're able to use APIs, we're able to use the language where we can shape the data. By transformations, I mean functions. So the main goal of this data pipeline was to make data queryable, right? We want as soon as something is, we're able to make it queryable so we can get value from that data. That was our underlying goal. And a big problem that we faced with Redshift, and a big problem that you'll face with most data warehouses, is the storage and the compute are not separate. What that means is the data is stored within the engine that is running your queries. So that is a problem when you've got your ETL running all the time, your analysts running queries to power the dashboards, but then you've also got a data scientist running a query against the history of the business. All that affects the performance of your dashboards. So you can't come in and say to like an analyst or a business executive or a stakeholder, the dashboards are running slow because this data scientist is running this horrible, horrible query. And Redshift tries to solve that by assigning queues. So this is 70% is for the analyst. They can't use more than that. 20% is for 25%, for example, is for the ETL, and 5% as a reload for scientists because they don't care how long it takes. But even then, if the queries are written badly, or even if the tables are designed badly, by designed, I mean the sorts and disk keys. This is how the data is partitioned in your data warehouse. If they're designed badly, the queries are still going to take too long. So we wanted to separate the storage and the compute. We wanted to run different clusters for different purposes. So this is the architecture we came up to. So we pushed things to S3 into our data lake, which was in S3. Right? And I'll show you later how the data's partitioned in S3. Then we have a processing cluster that does our transformations, and I'll go through that in a bit. But then we have a data serving layer, 2 different data serving layers. This Presto cluster is going through the data and saying, okay, this is for the analysts. You can query it via SQL just as normal. You have the only difference is slight syntaxes. Like certain functions that you think will work in Redshift might not work in Presto, and so on and so forth. But the standard SQL does. And then you've got a different data science cluster that's reading from the same data, but the compute is completely different. So you've got Tableau running into Presto if you can to get your dashboards, and then your SQL workbench if you have a data scientist, or even if you've got like a data analyst that just don't want to go through Tableau and want to run ad hoc queries. So that enabled us to separate. That was one of our biggest problems. But then we also wanted to be able to handle bad data. Now, handling bad data, because you have no control over the data that's being provided to you by your data providers, right? So although they'll just give you a dump of CSV, they can give you things like ints that are meant to be strings, give you things like booleans that are null when they're not supposed to. The more painful ones are when they give you timestamps in different formats. Instead of UTC, it's BST, or it's American Standard Time, or a date time column that comes in the format of the American Standard, which is year, day, month, instead of year, month, day. So you have to handle that and all these discrepancies that happen within your data. So how we did it is we aligned our schemas with our code. They're packaged up together. And before we start importing or processing the code, the very first step is validating the schemas is what we expect. Now, that's a pain when you're starting off and you don't know what the schemas are going to be, but it's much easier later on when you're actually running in production and you get a new batch job and it fails because the schema's not right. That's easier to catch because then you're alerting on it. So that's how we handled bad data. We always get the data we expect. The next thing is obviously schema updates. And this was a pain because us as engineers were lazy. We didn't want to be in a situation where we have to backfill six weeks worth of data because of a miscommunication. We wanted to be like, as soon as we call an API or as soon as we get a field that's new in a new column, we want it automatically ingests it and automatically amends the schema. And that's easier to do when you're working on a data lake because, again, it's just flat files. And another thing we added was alerting. You know, whenever something fails, whenever something's initially succeeded, because we wanted to get more trust in our pipeline, and we need alerting to add more visibility. Everyone knows. They actually, as soon as we released it to 15 minutes, all the analysts thought it was bulletproof. They saw no failures. But actually, the same failures were originally occurring before we moved to a data pipeline, but it was invisible to them because it's a bare core concept of fail fast. We fail fast, so the amount is 15 minutes worth of data, so it's very easy to recover, and everyone's aware of when it fails. So we added things like PagerDuty, SNS alerting to phone and to emails. And if you ever wonder if you're doing your best or your team's doing your best when it comes to maintenance, as soon as you're responsible for your code at 4 a.m. and you're going to be woken up, suddenly you're churning out amazing code. So stability becomes really important if it affects your sleep. So we wanted to handle different data formats. So the de facto formats that people give you as a third party are CSVs and JSONs. These are flat files. However, they are not very maintainable when you're trying to open a 20 gig CSV on your laptop. So things like Avra and Parquet are file formats to store it distributedly via columns, and I'll explain what Columnar Storage is. But we convert all the raw files to Parquet before we store them, and the difference between Columnar and normal row storage is in a traditional SQL database, you store the entire row together. But each row will have a different data format. So that could be a string or a varchar, same here, and then that's a date, and that's supposed to be a decimal because it's a value, or a long. So the different data formats you can't compress them very well because they're very different. But if you store the column alone, you'll know you'll always get a string here. All the values here will be a date time, and all the values here will be a decimal or long or a big int. So then if you store them just by the column, the amount of compression you can do is much higher. And hence you get smaller files compared to the original, and it's easier to manage. So this is the architecture of a data lake. So the raw files come in as CSV and JSON, right? And we don't do anything with them initially. We store them as they are. And the reason we store them raw is because in 8 months, if we realize we did a calculation or transformation wrong, we can go back in time and say, this was the original file that was given to us by the user. We can't go back to the data provider and say, look, remember you gave us this file 5 months ago. We made a mistake. We need it again. We can't guarantee they'll give it to us. So we store it as it is. But because it's not manageable very well, we then convert it to Parquet. As it is, same column, same field, same everything. It's just in a more manageable file format. We then data model it. So we convert it and we transform it into the shape of the business, the domain language of the business. So if a third party calls it transaction ref, it might be an order ID. A user reference might be the email address, for example. So the language or the language that's being written by analysts, or the column names that are being used by the analysts. And the last step here is not necessarily where everyone uses, because at that point there, you join them wherever you join all the tables you want to create your master table, and you load it onto your data warehouse. But remember, we don't load directly to a data warehouse. We have Presto running to look at the schemas in our S3 lake. So this is our end table, and this is a mirror of the table that's being queried by the users after joining everything you need to join. And again, we do this to separate the storage and the compute. We use Apache Spark because the main two things, it's an in-memory data cluster, and my demo will be about Apache Spark. But the main two things that give us, one is invisible to us as users, and the other is extremely visible. The first invisible part is it handles the distribution of data, and if a data node or a worker node fails or corrupts the data, automatically handles the copies being done by the different worker nodes. So all the very difficult problems with distributed computing, Spark handles to us for free. The second thing that is really useful and it's extremely visible is you can use 4 languages within the same processing engine. So you use Scala or Java, R, Python, or so PySpark, and finally SQL. So a variety of different skill sets can query the same data and query the same data within their different preferences or different language preferences. We also implemented DAGs, or what we call direct acyclic graphs. And remember, all the orchestration was originally done by the hard-coded ETL scripts. But orchestration saying, imagine you have a table, let's call this table Z, right? In the ETL scripts, we realize we've got 6 or 7 tables that table Z depends on. So it's a dependency tree. We have to do those 6 or 7 first before we do 7, otherwise it fails. What a DAG is really a dependency tree to say, before you do table Z, make sure all these succeed, because these are the dependencies of that. And a DAG, all its job is to schedule, retries. Things like retries, obviously, were done in the Python scripts, which were really difficult. But DAGs are we've used a scheduling framework called Airflow. It's Apache Airflow. And it says, you know, once you run all the trees, if something fails, retry it, back off, try it after an hour. And it's very, very simple to do. And it's much, much harder to code your own, because it becomes much more difficult when you then put things like data processing and transformations. So now that we've got all the data in data lake, our job's not done, because the data pipeline also has to be queryable. That was our underlying goal. So we have a data serving layer, which is our Presto cluster, where people can query it. That's our UI. People can query via SQL very simply, and also via dash if you want to go through Tableau. So that we used Presto, which comes with EMR, and then we want to transition it to Amazon Athena, AWS Athena. But if you ever used Athena, as soon as it came out in Europe earlier in the year, there's so many little frustrations with it that we didn't use it. So one is everything needs to be lowercase. The column names need to be lowercase, and that's just a nuisance, but you can do it. The next thing is there are data types it doesn't do. Like dates, it doesn't do dates. It does date times, it does times, it just doesn't do dates. So we said we'll back off till the new Hive, it gets a newer version of Hive, basically, which handles it, because Presto did fine. We have a Lambda architecture. And for those of you who don't know what Lambda means, it's basically where you separate the batch, which is a slow serving layer, things that happen once a day or once an hour, slow, versus the streaming, which happens every second, every microsecond. And streaming, you think of it as like Twitter, right? You don't want to know what's trending 6 months ago. You want to know what's trending now. So it's very short-lived data that's relevant for that amount of time. But we had problems with streaming because one is we need Kafka, which is the de facto streaming technology. So we go up to our CTO and say, look, we need a Kafka cluster. We need 100 grand to just develop this. And they were like, well, no, it's been working fine now. You have to validate that assumption, right? You have to validate that assumption. And it's a fair point. You can't go up and say we need this X amount because we need an in-memory. We need a Kafka team to deal with it. It's not a managed service from AWS or any other provider. And also, another issue with streaming is we have to think about things like retries, checkpoints, the consumer. So there's a producer and consumer. The producer of the data is someone tweeting. The consumer is someone reading or liking or retweeting. The consumer has to know where they were in the stream, and all the all the logic of that has to be done by the streaming consumer. So that's where actually, I'm just going to stop using this because it's really annoying now. So that's where Spark came in with structured streaming, which is supposed to handle that for you, where you can, they realize people don't just do streaming. They have applications running off these streams. They have things like running SQL queries off streams. They're saving them to a particular sink, which is like S3 or a database or so on and so forth. And finally, they want to do stuff with the streaming. So they come up with structured streaming where you're able to easily point it to a checkpoint directory, so it will handle failures. All you have to do is restart the stream. If you can have long-running streams, and so on and so forth. But we realized that Redshift was not fit for purpose because of the certain data that we have when we want to amend schemas, and that's where Google BigQuery came in. The certain members of the BI team have Google Analytics. So they have a very easy way of moving Google Analytics to Google BigQuery. Out of interest here, how many people have heard of Google BigQuery? OK, so good. So I don't have to sell it to you. The concept of BigQuery is whatever query you run, you're not paying for the cluster to be up, like Redshift or a Presto cluster. You're not running it, or you're not keeping it up. But you're paying per query, right? So you pay about, I think, about $35 for 1 terabyte, but it will always return within seconds. I have yet to write a query on Google BigQuery that returns more than 2 minutes, regardless of the size of data, because whatever query is run on Google's hundreds of thousands of virtual machines, it comes back. So it's very, very, very cheap to prototype something with a large set of data and quickly find out the benefit. But the reason we migrated to BigQuery is because then we can, when we're saving things with new schema updates, it automatically picks it up, and we can save JSON directly if we wanted to. And it's very easy to pick up new columns, and you'll be able to query that. And I'll show that in the demo in a second. Problem we face is there's no Spark connector for BigQuery. There isn't one. So I wrote one. And the way it works is the more painful is you can't save Parquet directly to BigQuery. You can save JSON, CSV, the raw files, but you can't save Parquet. And all we used was Parquet. So we wrote one, and you can check it out there in GitHub. And it has all the features that Spark uses, like structured streaming, PySpark. So it's very easy to get through. So have a look at it, and PRs are always welcome. But that allowed us to write machine learning recommendations. And the first recommendation engine I wrote was we have the order information, right? We have users' information to what orders they're making, what restaurants they're making, what they're watching, for example. So to give you an example, say there's a website that sells clothes, right? Women's clothes. And on the weekends, I decide to call myself Samantha and dress up in women's clothing. So I can be using this website where I buy 9 items, right? And then there's this another person, same age or slightly older, that buys 10 items. Now, if that person's 10 items are the same as my 9 items, then we have similar tastes. So the 10th item, I'm more likely to buy. So we use all our data to create a matrix to say, OK, these same people have to see similar interests, so we'll provide recommendations based on that. It's very similar to Amazon's people who bought this, also bought that, but it's tailored or personalized to you and your interests. And you only need 3 things to do that. Completely simple. You have a product ID, a set of users, and a set of what they ordered, and a set of, that's it, a set of users and a product ID, really. And then it will try and do a matrix for it, and the ALM metrics. And that is Spark MLlib. So it's very simple. You can Google it. It's fine. So now for the demo. So for the demo, I wanted to, let's mirror things first. So let's mirror the displays. Yeah. So the demo, what I wanted to show you was a simple JSON document, right? So I'm treating my hard disk as a data lake, but it doesn't matter. That's not very viewable. So let's copy that to, yeah, I've got a JSON lint here. So that's a JSON, right? And a JSON could be it could be nested. And you've got this being returned by an API. You know, there's things, metadata about the information of the user, a legacy order ID, the containers being, you know, what user agent they've been using, and the order information. It's a massive JSON that's very simple. Now, the API returns that, and your goal is to make that queryable. And I'll show you the code in a second. But it's very, very simple. My code, well, Spark allows me to do this, actually. But what I'm doing there is I'm reading from my data lake. Again, this could be S3. You can point it to an S3 directory. And what I'm doing is I'm going to say everything that comes within this data lake, I want you to read it in as a data frame, which is a data table. And I want you to infer the schema. I'm not going to give you a schema. You can define a schema if you want, but I don't want to give it to make it simple. And then finally, write it to a table, which I'm going to call Øredev demo. And here's where I want you to store the checkpoints. So you go there if you fail, or if you stop. And that's it. That's the majority of the code. This is just to start Spark. So if I zoom out, you'll see that the main function is really, really small. It starts from here, ends there, right? And what it's doing is looking at a data lake. Whenever a new file comes in, reads it into a data frame, saves it to Google BigQuery. So if we then run the, just check if the file is in the data lake. Yeah, we've got that same orders file, which is that JSON file. And I'm going to run that. So what it's going to do is going to spin up a streaming application. And it will, once it starts up, it was going to continually look at that data lake orders. And again, that could go to S3 if you want to. And you point it to a particular topic or a particular stream. If you're using AWS Firehose, you can push your events to a certain S3 directory or path. And it will hopefully, oh, the internet's really slow. Right, I'm going to have to reconnect to the network. No, it's working there. So what it's doing now is just starting to spin up, getting the Google authentication. And then it just says, OK, where am I? Oh, I got, this is what the schema looks like of the file, of the data frame once it reads it in. It looks at the GCS working directory. So GCS is Google Cloud Storage. It's the same as S3, really. And then I'm going to be like, oh, I picked up a file there. That file is called orders. I found a new file. I'm going to start, create a table, or a dev demo. So if we go down to BigQuery and refresh, there's nothing in that test data set. So if we try refreshing, we should see a table being created, right? And there you go. It's got one record in it, right? And now I can write a query that's saying I want the nested, let's say, application info. Is that there? Application info user agent. So that's what, two nested levels down. And if I run that, nice. So this is standard SQL, and so you can preview the table. Yeah, the internet's really, really slow. There you go. So is that what it is? Maybe. Oh, what have I done there? Yeah, there. Application name. So what happens if we come up to the situation where the company decided to do Facebook login? So I've got the same file, but now it's returning, is Facebook login true? So just so I don't trick you, when you're amending the schemas on Google BigQuery, where is the schema? So if we refresh that, very, very, very slow. Okay. Right. So what I'm trying to show you here is the schema of the table in BigQuery. So that allows the users, like a data explorer, allows the users to look at the schema, but it's just tremendously slow. Right, so while that's loading, what I've done here is added the Facebook login true, and then I've got the new folder here. Right, so what I'm going to do is stop that query, and then copy the orders into the data lake, which is here. And have that loaded yet? No, this is ridiculous how slow it is. Should I try reconnecting? Right. Yeah. Right, so what I'm going to do is I'm going to start the streamer. And what it's going to do is it's going to say, now there's 2 files. However, according to the checkbook directory, the last batch I wrote to BigQuery was batch 0. So I'm going to ignore the first file, and I'm only going to look at the second file. So if we, yeah, it's really, really slow. Waiting for the batch IDs to come up. Oh, there, it picked up the batch ID, right? That was the batch 0. And then it's going to say, OK, I'm going to continue where I left off. And when BigQuery loads, I can show you that the table was amended with is Facebook login. But I'm not quite sure why the internet's really, really bad. There you go. Now it's loading. That one loaded. No, it did not. Oh, that's great. Well, while that's loading, feel free to ask any questions if you have any. If you have any questions on the code, again, the code's on GitHub. So is the connector. Does anyone have a question so far? No? OK. There you go. So there you go, Øredev demo. So you can see that the is Facebook login is not there yet. So if I refresh the page now, maybe it's here. No, yeah, it still hasn't copied it because of the internet. Right. OK. So I'll give that a few minutes. And if you, does anyone have any questions? All right. Well, thank you very much for listening to me. And apologies about the internet.